Appendix 1.1, Real Numbers and Absolute Value. The natural numbers are what you would refer to as the counting numbers. They are integers and we start with 1. These are actual items that you would be able to total. Whole numbers are the natural numbers and also 0. Integers include also the negative numbers. Rational numbers are real numbers that can be written as a ratio of two integers, P over Q, where Q does not equal 0. Remember, we cannot divide by 0, so it cannot be the denominator for a fraction. This set includes all integers and repeating or terminating decimals. So any decimal that terminates or any decimal that repeats forever would be included with rational numbers as well as integers. Irrational numbers are going to be your real numbers that cannot be written as a ratio of two integers. This set includes all infinite non-repeating decimals. So the square root of 3, 2.4584867, and then it keeps going just with random numbers. Pi is an irrational number, and so is E. I don't know if you guys have gotten to that in science, but E is another irrational number. We are going to be looking at distances between numbers today, so we'll be glancing at number lines and also looking at inequalities. So an inequality would be something like -3 is less than or equal to x, which is less than 1. To write that in interval notation, which we'll be doing in this unit, you would use a bracket where we had a or equal to with our inequality, and then we use parentheses where we had just the inequality part, the less than, greater than, and not the or equal to piece. So that means that -3 is actually included in this set, but we can get close, really, really, really close, 0.999999999 on forever. So we can get really close to the number 1, but the number 1's not actually in the set. So the description is all real numbers greater than or equal to -3 and less than 1. We're going to be looking at absolute values because we're going to be looking at distances between two numbers, and we know that distance is always a positive value, so we must make sure that we remember how to handle absolute values. So if we have an absolute value of -12, absolute value means we want the positive of whatever is inside of the absolute value bars. So if our quantity is -12, the absolute value of that is +12. If our absolute value is positive 5/8, then our value is 5/8. If we have negative absolute value of -5, that's like having negative times +5 once we use the absolute value bars to evaluate what's inside. And you would do that first, following order of operations, because absolute value bars are considered a grouping symbol. So we end up with -5. So in order of operations, we know that we handle, they say parentheses, but parentheses means any grouping symbol or any group. So it could be an operation that's inside parentheses. It could be an operation that is the numerator of a rational function. And it can also be absolute value. So we're going to have to determine the absolute value of -7 and 3 before we subtract. So we get +7 for the absolute value of -7 and then 3, and so our answer is 4. Our last example, we have -7 in the numerator and we have the absolute value of -7 in the denominator, which is +7, so we end up with -1. Distances between two numbers. So this D here in italics is representing distance between the numbers -37 and 55. So you can subtract these two numbers from each other in either order as long as you use absolute value bars. So we can do -37 minus 55, which what we would do with that, of course, is make that an addition of a negative number. And together we get -92. So the absolute value bars, like I said, are a grouping symbol. You're going to have to perform whatever operations inside the absolute value bars that you can before you handle the absolute value. And so we go ahead and make that arithmetic operation before we say that the final answer is 92. We can also say 55 minus a negative 37, so it really doesn't matter. This ends up being adding a positive. We end up with the absolute value of 92, which of course is our answer of 92. The distance between negative 87 and negative 13. Again, we can subtract in either order. Negative 87 minus a negative 13 gives us a negative 74, and the absolute value of that is 74. Negative 13 minus a negative 87 is basically going to turn into a plus positive 87, so that gives us the absolute value of positive 74. And of course, again, we get the same answer. So you can choose to subtract the numbers in any order that you like. 124 and 358. So we can say 124 minus 358. Make sure you put the absolute value bars there. Or we can do the absolute value of 358 minus 124. So you're going to see questions that'll say use absolute values to determine the distance between two numbers. Even though in this second example, or the second way I wrote it, I have a positive 358 minus 124, which we know is going to be a positive number, you still need to set it up with the absolute value bars. So up here on top, we get negative 234 in the absolute value, so that means 234 is the distance. Down here, we get positive 234 in the absolute value, which is what we expected. And of course, the absolute value, that will be positive 234. So we have one more example to cover today before I let you go, and that's going to be absolute value inequalities. So we don't know necessarily when we have a variable inside an absolute value whether or not what's in the absolute value is a positive or a negative. And the reason is that it can change. As long as x is not an undefined number, I can put anything in for x. So I could put 27, I could put negative 1,000,002, I could put anything I want. And then we would have to determine whether or not the inequality is true. So how do we know whether or not what's in the absolute value is positive or negative? Again, we don't. So how we're going to handle that is by writing two inequalities. We're going to say that x minus 3 is less than or equal to 5, and we'll consider this to be our positive inequality that we create of the original, and then we're going to have a negative of the inequality. And so when we do the negative, we're still going to leave x minus 3 the way it is, because remember, when it comes out of the absolute value bars, it's going to be positive. It is the other side of the inequality that we have to adjust. And so we are going to change the sign to greater than or equal to. So we change our inequality sign, and we also change the sign of 5 and make it negative. So let's go ahead and solve these just like we would algebraically. We are going to add 3 to both sides of each inequality, and we get x is less than or equal to 8, and x is greater than or equal to, add 3, that does not look like a 3, negative 2. We have the or equal to part, so this is a bounded interval. We would use brackets to denote it in interval notation, and we would list the more negative number first. So negative 2, 8. And that's the way we always do that. The more negative number is going to be on the left, just like it is on our number line. To graph this on our number line, we can use closed dots or brackets. I like using brackets because it's just like the interval notation. So you use a bracket on 8 and then where negative 2 would be. And for this one, we are shading in between because we have an x is greater than or equal to negative 2 and an x is less than or equal to 8. So that means this can be written as a compound inequality that would look like negative 2 is less than or equal to x, which is less than or equal to 8. So that means 8 can take on any value between -2 and 8 inclusive. Since it is bounded, the endpoints are included.